I would like to extend my heartfelt gratitude to Professor Sharma, Professor Joshi and Professor Shivakumar for providing me this opportunity to present in front of you at a very early stage of my career. And I very recently interacted with Professor Sharma while his visit to IIT Roorkee, and the way he shared his knowledge and wisdom with such generosity, so I am very grateful to that. So today I will talk about this transition to electrocatalytic refinery and refinery, that is e-refinery basically. So Professor Tara has said very good background was what is the demand for global energy and why we require the renewable energy sources, what is the requirement of green energy, what is the electrochemistry and these things. So they have said the very good background on that. So e-refinery, that is electrochemical refinery. So this is basically the accelerate the transition towards sustainable fuel and chemical production. So I am not going into the detail of this conventional fossil fuel based refinery with the comparison of e-refinery. I am directly switching to the e-refinery. So yes, I am talking about complete conversion systems, which in our group we are mainly focusing on. So if you talk about, here I am referring to two types of conversion. One is the indirect route and the second one is the direct route. So indirect route basically refer to the, we are taking hydrogen from the electrolysis and then we are converting this, using this hydrogen, and we are utilizing this hydrogen in a thermal conversion process. To converting, using this hydrogen and CO2, we are converting it into the value-added fuels and chemicals. So that is the one approach. And right now I am focusing on the second approach, that is the direct one, electrochemical conversion. So can we directly convert CO2, or Professor Tara has already mentioned, can we fix the nitrogen to ammonia using the direct electrochemical conversion approaches? So but there are challenges when we talk about the electrochemical conversion approaches. That is a lab scale study, how to scale up this from the lab scale to industry scale. Right now we are using mainly the batch reactors. How to scale up from the batch reactor to flow reactors. What is the catalyst electrolyte interface? What is the catalyst stability is a big challenge when we are exceeding the process from the batch reactor to flow reactor. So these all are the issues which I am mainly talking about. So parallelly we are working on the both routes, this indirect route as well as the direct route. So indirect route where we are directly taking the hydrogen and converting the CO2 to methanol dimethyl ether for So CO2 to methanol, dimethyl ether, ethylene, formic acid, ethylene, so all are the value-added products and chemical. In my talk today, I will mainly focus on CO2 to ethylene, as ethylene is a very good market size. And if you talk about the petrochemical industry, we can directly utilize the ethylene. So these are this slide is basically referring to the possible scenarios for electrocatalytic bond cleavage towards a key chemical. So if we see this Venn diagram, so here there are different carbon sources which we are utilizing, that is basically on the CO2, methane or biomass. And then if we see the possible bond cleavage, then CC bond is there, CH bond is there, CO is there, CN is there. So we are mainly focusing on this CC, CN, CO bond, OO is there directly, NN is there for fixing this nitrogen to ammonia, NH bond is there. So we are trying to focus on the cleavage of these bonds through the electrochemical route, purely on the electrochemical route is basically, and we are trying to avoid this thermal conversion, because the beauty of this electrochemical reaction is we can accomplish the reaction at the ambient conditions. And similarly I am showing this energetics, so you can directly see, because one thing is CO2 capture and other thing is utilization of CO2 to value added fuels and chemicals. So I am trying to integrate both CO2 capture and conversion in a single reactor. So how you can capture the CO2 and then converting it into the same reactor to minimize the unit operation, that is the one thing, and to intensify the process basically. So these are the major products which we are focusing right now. So CO2 to CO, formic acid, methanol, and if we talk about the C2 product, then ethylene and ethanol. So these are the major products which we are currently focusing. And from methane also, this methanol and ethylene is there. From nitrogen, ammonia is there. So right now I am focusing on this part, this CO2 to CO intermediate is there, and then multiple C1 and C2 products are there. And this table is showing the equilibrium potential, that is the thermodynamic calculation for CO2 to different products. So we are trying to disturb the thermodynamics of the process. So these are the principle and strategies for the design of electrocatalyst. So when we talk about the electrocatalyst, so there are multiple things comes into the picture when we compare it from the different catalysts. So one thing is the role of electrolyte. So role of electrolyte is very important when we talk about the CO2 conversion, because CO2 conversion, when we talk about the CO2 conversion through electrochemical route, so what is happening here, that CO2 requires this acidic environment and basic environment. So when we talk about this KOH and KHCO3, so these are the general electrolyte which people are using right now. But what is happening there, the controversy about the role of bicarbonate is there, because when 1 mole of CO2 is converting into the 1 mole of ethylene, at the same time 6 moles of CO2 is getting converted into the bicarbonate. So there are two approaches. One thing is we can utilize it at a CO2 capture and conversion in a single pot, and the second thing is if but it is happening at the cost of compromising the yield of ethylene. So the second way is, can we eliminate this formation of this SCO3 minus, one thing, and the second thing is, or we can increase the yield of ethylene. So that's why we are utilizing this different kind of alkaline earth metal, lithium, sodium, potassium, rubium and cesium. So we observe that as the size of atomic radius and the size of this cation is increasing, so this is suppressing the role of HCO3 minus, and this is how we can utilize the reactant amount, because when 1 mole of CO2 is converting into the 6 mole of ethylene, at the same cost we are losing this CO2. Reactant is we are losing this reactant, and it will affect when we do the calculation of conversion or selectivity and everything. So right now whatever papers are publishing, so they are not reporting the CO2 conversion basically, or if they are reporting the CO2 conversion from the electrochemical pathways. So what is happening there, it is very important to mention where we are considering this loss due to the bicarbonate, or we are excluding it, or we are converting it, because ultimately it is affecting the yield of ethylene. And if we see the role of this local CO2 concentration and pH gradient is also very important. So local reaction environment is affecting, because when we do the reaction, so what is happening, after like 4 or 5 hours of reaction, catalyst gets released from the surface of the reaction due to this disturbance of local pH. So what we have done, so there are 3 approaches. First thing is we can do at the constant voltage experiments, or we can do the experiments at the constant currents. But when we are doing the experiment at constant voltage and constant current, what is happening, we need to replace the catalyst after 4 or 5 hours. So, and this is the major challenge when we talk about the electrocatalytic stability. So long-term stability is the major challenge to utilize this at an industrial scale. So what we are doing, we are following the approach of pulse electrochemical. So what we are doing, we are doing the reaction for 4 or 5 hours at a constant voltage, and then for a very short time we are impulsing the current on that. So it start restructuring of the catalyst start over the surface, and again it gets activated for 4-5 hours. So this cycle we are repeating for like 4 or 5 times. So it gets a stability of 20 hours or 30 hours. This is how it is increasing the stability of the catalyst. And if you talk about the this process diagram, so there are 2 steps. First is the CO2 to CO conversion, and the second step is CO to ethylene conversion. So this is the one approach, and the second approach which we are targeting, that is a tandem approach, where we are directly converting this. This is the tandem approach, and we are also targeting this CO2 to ethylene in a single step. But the major drawback of the major challenge we are focusing there is the how to control the formation of salt formation, bicarbonate formation. And in this approach we are getting the good yield, Faradic efficiency up to 85%, and good CO2 conversion is there. So parallelly we are trying both the approaches, and we are trying these approaches in the H cell as well as in the batch reactor as well as in the flow cell, all these reactors. And conventionally, if you compare the ethylene, then steam cracking of ethane, it is a conventional process to produce the ethylene, which is very energy intensive. And if you talk about the CO2 emissions, so 150 million ton of CO2 is emitting, that is the second largest after ammonia. So we are trying to replace this well established conventional process with electrochemical CO2 conversion to ethylene. So this is our approach from the transformation from the lab scale to industrial scale. We are targeting these parameters which are directly affecting the performance at the industrial scale, and parallelly we are trying to increase the how to decrease the stat and how to increase the electrochemical surface area. So both the approaches we are parallelly trying. And the second one I have already explained, that simultaneously conversion and capture in a single reactor. So this idea I got where the loss of CO2 bicarbonate is there when we converting it into the ethylene. So I got the idea from there, can we utilize this approach for direct conversion and capture and conversion in a single step. So this is how it is driven. So the major challenges is that, so how to get this batch reactor experiments into the flow reactor, because stability is the major issue here. Like catalyst is stable for 20 or 30 hours only. And the second thing is how to get the industry relevant current density, that is around 200 ampere per centimeter square, or the Faradic efficiency greater than 80%, purity of ethylene. So these are the major challenges which currently we are focusing, we are targeting. That's all from my side. Thank you. Now open for questions.